this computer. Okay, the next one that we're going to look at is sample problem 13-2. This looks kind of familiar. We've looked at similar problems previously, but this time we're going to be using that work energy theorem, and we are going to be looking at these two blocks and solving for, what am I going to do? Determine the velocity. Yeah, I was looking here. Where is it? Where is it? So we have two blocks. They're joined together by a cable. And if the system is released from rest, determine the velocity of block A after it moves 2 meters. Assume that the coefficient of friction between block A and the plane is 0.25 and that the pulley is frictionless and weightless. So we don't have to worry about anything over the pulley. We're just concerned about the block in contact with the table here. And then here we have block B, which is 300 kilograms, and block A is going to be 200 kilograms. So let's start our problem first by identifying the items that were given and then what we're going to be solving for. So this is sample 13-2. Okay. Now, our convention is going to be a little bit different for this one. Okay. Because we have that freedom of changing our convention as like the problem seems to make sense, we're actually going to have our convention where the X is going to the right as standard, but because we have that block B falling down, that's going to be assigned as the positive direction, if you would, for block B. Okay, just kind of eliminates some of the negatives that we would get otherwise. Now, what we're given in our problem is the coefficient of kinetic friction, and that's going to be 0.25. Okay. Our distance is 2 meters. That's what we want to know, what the velocity is after it's traveled 2 meters. As far as what we're going to find, okay, we are going to find the final velocity, okay? Because the final velocity is going to be the same for both blocks A and B. So we don't have to separate them out because they're joined together by that cable. So it's going to be the velocity after, if you would, or at that 2 meter mark. Okay. So let's start by looking at block A. Okay, block A. We are going to use the work energy theorem. So I'll just put that up here just so that we let's see it. T1 is equal to, or I'm sorry, T1 plus work 1 to 2 is equal to T2. So this is really what we're going to be looking at for each one of the blocks. So we're going to do work and kinetic energy for block A and then work and kinetic energy for block B. All right, so block A. Okay. Let's first draw our blocks. So we're going to have block A. This is going to be position number 1, and this is going to have a positive direction going to the right. Okay. The weight of block A is M times G. We know that it is 200 kilograms. Okay. It's going to have a normal force here, normal force at A. Now there is that cable that is connected to it, and that's a force that would be pulling it to the right. And we're going to call that FC. That's going to be the force in the cable. And then this block also experiences, going in the opposite direction of the motion, it experiences a friction force. Okay. Now, this is going to be position 1. So this is going to be considered V1A, if you would. It's equal to 0 because this is where it starts. Then we're just going to draw this 2 meters down the way. Okay, so this is going to be 2 meters. All right, and this is going to be velocity 2. And I want to know, what is that velocity? And this is going to be the 200 kilograms. This is block A. Okay. Now, I'm going to solve for that friction force because I know what I need. I know that the kinetic coefficient of friction is 0.25, and I know that my friction force is going to be equal to that coefficient of kinetic friction times the normal force at A. Okay, it's always how you calculate a friction force. So we can say that we're going to sum our forces in the y equals 0, just statics, so that we can say our normal force at A minus the weight at A is equal to 0. So we can say that the normal force at A is equal to WA, and that is equal to mass times gravity, right? I'm going to be going down again here, which is going to be 200 kilograms times 9.81 meters per second squared, which is acceleration of gravity. So our NA, all the way down here, is 1962 newtons, okay? 1962 newtons. That's going to be the number that we put up here, okay? So our friction force then is going to be equal to 0.25 times 1962. Our friction force is going to be equal to, let me know what you got. You guys get the same numbers? Does that make sense? James? 490.5. Yep, 490. Thank you, Lex. 490. I'm going to go with 0.5. That's what I had on my paper too. I kind of held that extra decimal place for a little bit more accuracy inside here. So that's going to be my friction force. Now, as we look at that equation for the block, okay, we're going to say the kinetic energy 1 of our block plus the work 1 to 2 of our block, so that's why I'm putting the A's here, is equal to T2 of block A, all right? Now, this is going to go to 0 because the velocity is 0, so no kinetic energy on the T1A, all right? But we will have kinetic energy because we're actually going to be trying to solve for that velocity as part of our problem, okay? So we've got our two parts, okay? We've got our work and we've got our kinetic energy for this block that we have to reconcile, if you would, and then plug it back into the work energy theorem. So let's look at the work of block A first. Okay, the work of block A. So the motion of block A is going to be horizontal. So to define the force over the distance, it's going to be the horizontal forces are going to be the ones that are going to affect the amount of work. We've got two horizontal forces. We've got a cable force and we've got a friction force, okay? Using our positive convention here, we're going to say the work 1 to 2A, okay, is equal to plus or minus F times D, which is equal to, we're going to first have the cable force times that distance, okay? And that distance we're going to substitute in just a little bit. That's going to be 2, okay? Or I'll put it in here now because we don't know what FC is. We're going to put 2 right there, all right? Now, as we look at the direction of FC, notice that it's pointing to the right. So that means that that one's going to be positive out front, okay? And then we're going to have the friction force. The friction force we know to be 490.5 newtons. And we're going to multiply that by 2. But notice the direction that it's pointed in. It's going back in the opposite direction. So that's going to be minus 490.5 times 2. Okay. So solving for the work here, 1 to 2A, it's going to be 2FC minus 981. Okay. So we've got our work, if you would, in terms of that cable force. So we're going to kind of let this one sit. Okay. Now we're going to look at the kinetic energy of block A. Okay. All right. So we know that the kinetic energy 1 is 0. So we're going to be working on kinetic energy 2. Okay. So kinetic energy 2, T2A, is going to be equal to 1/2 m, the mass of block A, times velocity 2. Okay. And we're going to square that value. Okay. So that's going to be equal to 1/2 times 200 kilograms times V2 squared. All right. So that means that T2A is going to be equal to 100 V2 squared, or velocity final squared. And we have to leave it there in terms of that velocity. So if we look in terms of work energy theorem, okay, we can say that the work 1 to 2 is going to be equal to T2A, which is 2FC minus 981 is equal to 100 V2 squared. Okay, so we've got two unknowns here, right? So we can't really solve it. Right. So we got to look at block B, right? We've got another block. Yes. Move it this way or this way. Up a little bit, this way. Is that helpful? Okay. Okay, so let's look at block B. Okay, block B. That's the other part of this because it's connected to that, but with a cable to block B. And that'll help us out. So block B, all right. So we know that in this case, we took our position, our convention, and we said anything going down is going to be positive. So just as a reminder, I'm kind of re-putting that here. So position 1, okay. And our velocity B, just like it was for A, is going to be 0. We're starting at rest, but we're going to show our block B here. It is connected vertically with that cable force, and its weight going down is going to be here at B. We can calculate that weight. Might as well do it right away as long as we're here. It's going to be the mass of B times gravity, which we know is equal to 300 times 9.81. So our WB is 2943 newtons. Okay. And then the second position, kind of show it down here, this is going to be 2 meters later, right? We want to know, what is that velocity 2? Okay. It's the same velocity to 4A because remember, these are connected by that cable. All right. And this is going to be block B, block B. I'm just going to put 300 kilograms. Okay. So looking at this, we're using that work energy theorem, we're going to have T1B plus work 1 to 2 between those two positions is going to be equal to T2B. All right. So this is kind of our base equation that we're working with. Now T1B, because there is no velocity, there's no movement, there's no kinetic energy. So just like on T1A, that T1B is going to be 0 as well. Let's look at the kinetic energy. Whoops, kinetic energy of this block B, okay? So that's going to be the T2B, 1/2 the mass of B times the velocity 2 squared. So we know that the mass of that block is 300. So it's 1/2 times 300 times V2 squared. So T2V is going to be 150 V squared. I think I can squeeze the work in next to it. There's kind of a lot of space here. So work, block B. Okay. That means U1 to 2 is going to be equal to plus or minus F times D, right? So we look. The work being done in this case on the block, because it is moving vertically, is going to be the forces that are vertical. We've got two forces here that are vertical, right? So we're going to use those, and we're going to use our convention as anything going down, in this case, is positive. So our work here, our first force is going to be the 2,943. That's the weight going down. It's going in a positive direction. And we're going to multiply that by 2 meters. Minus, and I put a minus for the FC because it's pointing up. It's going in the opposite direction. So FC times 2. So our work 1 to 2 is going to be equal to 5,886 minus 2 FC, right? So this is the work part. Okay, questions so far? Good? All right, now we are going to insert these two values into our work energy for block B. So that is going to be our work side first. Is going to be 5,886 minus 2FC. It's going to be equal to T2B, 150 V2 squared. Okay. And then what we can do is we can add to it the equation from before. So we can say plus, okay, plus, we go back to our original equation from before. You remember, we had 2FC minus 981 is equal to 100 V2 squared, okay? So I'm going to line up the like terms here. So I have negative 981. So I'm going to add negative 981 to put it underneath the whole number here. And then I'm going to have plus 2FC is equal to 100 V2 squared. Now notice that our two FCs cancel out, right? One's positive, one's negative. So that's not gonna come along down. But then it's over here. We should get 4,905. When we subtract those two, it's going to be equal to, adding these two, 250 V2 squared. So now we have one unknown variable. Okay. So we can divide both sides by 250. And our V2 should come out to be, you have to take the square root of 19.62-ish. Check my numbers here. And what do we get for a final answer for V2? 4.42. Yeah, you got it. 4.429. Yep, 4.42, 4.43, Lex. Excellent. Meters per second, right? Those are going to be our final units. And that is what they were wondering. What was the final velocity of block A, which is still the same velocity as, and so is velocity B. Okay. So work energy theorem. I'll kind of back this out a little bit. Any questions at the moment on the second sample? In this case, they did, so we were able to add those together. Otherwise, what's the other way we could solve for this? Two equations, two unknowns. Yeah, that's what we would have had to do. But because that worked out, it's kind of a nice little shortcut when you recognize it, but we still will get the same answer. Yeah. Any other questions? Okay. It's almost like you wanted to do two equations, two unknowns, didn't you? Oh, hold on. If you know the tension in the cable doesn't change in both blocks, do you have to add it? Nah, technically not. That's another assumption you could make. Yeah. Yeah. Okay. Then what I'm going to do is I will stop the recording and we'll